Okay, so this is the next video in this series of bonus videos. We're going to talk about the critical stress. So at the moment we've got a critical force which we have found by looking at boundary conditions of our solution to a second order partial differential equation. And we've got an equation in this form here where L is effective. We've seen that L effective can be these various lengths. So we're going to rewrite this either using a constant on the top or on the bottom. Sometimes we'll use it modifying the L. So you'll find in various textbooks this written as maybe C pi squared EI over L squared, where L is the actual length. What does Arnold do in his notes? Sometimes you'll see this C to become an like a constant squared, and in Arnold's notes we've incorporated C so that we're modifying our L. So we're going back to this effective length kind of idea. So I've got pi squared EI over K L. And I'm going to square all of that. Okay, and then you've got this chart of K values that you can use. I discussed about in the last video. So that's the approach that Arnold's using. Righty. So the problem is that stress engineers don't like to work with forces, internal forces. They like to work with stresses. So how can we convert this so that it's going to be a critical stress? So the first thing I do is I'm going to introduce the radius of gyration, which is given as the cross-sectional area times by Rg squared. So I'm going to use an Rg here to represent that it's not the actual radius, but something called the radius of gyration. And if we substitute that into our equation above, we're now going to get it in this form. So we notice that although this radius of gyration term is a length, we've got a length here, so it looks like we've got a ratio of lengths. The radius of gyration, you could do a rough calculation to work out what it's going to be like typically for a column that's cylindrical like that, circular like that, sorry. So look it up in a book. You find that I is pi d to the power 4 over 64. So you say, well, what's the cross-sectional area for this? That's going to be pi d squared over 4 multiplied by, so that's my area, and then multiplied by the radius of gyration, K R squared. So we can see that the D2 is going to be the D4, it's going to become a D2 by cancelling out there. So we have a D2 there, and that 4's into 64 goes 16. So we have the pi's will cancel. So we end up with D squared over 16 equals Rg squared. So Rg equals D over 4. I mean, this is just going to be the case for when we've got a circular sort of a column being squashed. So if I was looking from above, we've got the diameter here, and then we've got our Rg, which is going to be a quarter of the radius. So it's this sort of length. So Just to get a rough handle on it for this kind of shape, we can see that RG and radius seem to be connected. They're not exactly the same thing, but they're certainly connected. So when the radius is small, then the RG is going to be small. So if I rearrange this, and I'm going to bring the RG on the bottom and then make this the ratio of the length. So I could bring the K in here, K L over RG, like that. Then I'll take out the K, so we've got K squared, real length for the column divided by RG squared. And this factor here, this L over RG, is called the slenderness ratio. Alright, so if that's somewhere between 20 and 100, then you're going to be more than likely you're going to be in a transition between something that we would structurally consider to be short and stocky to something that's long and slender. So if you're looking at L over RG ratios certainly above 20, then you need to start worrying that your structure of your column is going to collapse, not by it getting squashed, but by actually just buckling away. So you can now rearrange this so that we get the area onto the left hand side. So I've got P critical divided by area, so that's I can call that my critical stress, and then I can examine my equation. So I've got pi squared, that's a constant. Young's modulus of my column that I'm trying to squash is going to be constant. We'd obviously have to work out what our K term is, how we would define that in terms of structurally, how that's defined. And then we've got just L over RG squared. So the stress is getting less and less, the stress is getting more and more as the slenderness ratio goes, is going to go down to 0. Yeah, so if this starts to approach 0, then the critical stress for it to buckle will go off to infinity. So what I'm saying there is, if I make my column short and stocky, I'm not really expecting it to buckle. If I make my column long and slender, then the critical stress required for this to buckle is going to be quite low, because this ratio, this L divided by the RG, is going to be a big number. So 1 over big number squared gives me a little number. So I can plot that, and my critical stress will be something that looks like this. Yeah, so it's a y over 1x squared type function. So for the thing to go get structurally be unsound, we can see that it's not going to buckle when we make our column nice and short. So if we make the L nice and short, then it's not going to the stress will not be buckling. But if we now consider what's the stress where we're going to run into structural problems, well, we could probably say that we don't want the stress in our short and stocky column to be going above the yield stress. So most people would do a cutoff at yield stress. So let's say this is yield stress here. That's your stress value at yield. And then this we'd combine these two sort of plots together, and we'd say anything above this line here, we're going to have problems. Here we're expecting it to buckle, and here we're expecting it basically to get squashed, compressed straight downwards. The structure, the internal structure, will just kind of fracture and shatter everywhere when the stress goes above there. Okay, so that explains the critical stress term we've got.